Man, this sucked. Friction is one of those things like manual breathing, where you don't really think about it, but when you do, it's the most horrible thing ever. Despite the fact that I overhauled the entire physics system to implement it, friction was still the hardest thing to do. I won't go into too much detail about how the system works now, but here are some things you need to know about it. First, the system is broken into 3 stages, injected into the Unity pipeline directly after the time update. This allows me to decouple the system from Unity's fixed time step and more concisely separate each event. The 3 very namely events are the move update, check update, and resolve update. Move update calculates all the acting forces for every simulated body, and then applies them to its position. The check update takes those newly acquired positions and searches for any potential collisions. Every collision found is stored in the list of collision data objects, containing things like collision normal, penetration depth, the colliding object, and so on. Last but not least, the resolve update lets the physics body iterate through its collisions and find implementation-specific resolutions for them. These subsystems are good, but there should be one more: the impulse resolution update. This subsystem would allow for a physics body to do velocity changes that can only occur when colliding with another object. If you know anything about physics, or read the title, you probably know that I'm talking about friction. At the moment, friction is being calculated as any other force, which is not ideal. Going frame by frame, you can see that for exactly 1 frame, friction will not be calculated. Because the collisions haven't been checked, the friction component has no normal force to base itself on. After this frame, the collision data is there and the friction component is free to do its calculations. An issue I struggled with for a while is when applying the friction, it seemed to never fully negate the current velocity. Therefore, the current implementation only really accounts for the friction along a slope with no external forces applied. As for the method of applying friction itself, first I set the local gravity member to whatever the gravity component's g-force is at that frame. This allows for dynamic updating of the gravity, much like the style of Super Mario Galaxy. Next, I check if the body is colliding with anything and reset both the friction force and the normal force if it isn't. Again, friction can only be applied when colliding with something. After setting defaults for the normal force and a value n.g, which I will get to later, I iterate through each collision for the body and compare its n.g value to our existing one. We're trying to find the lowest one here. The reason we want the lowest value for this is because we want to take the collision normal that's facing the most opposite to our current gravity vector. An example of what could go wrong is if we are colliding with a plane that is facing the exact same direction as our gravity vector, the following calculations could not be physically accurate. Once our lowest n.g is found, we take the found normal force and multiply it with this value. Using this new anti-normal, we can find which way the friction is being applied by subtracting the gravity component from it. The magnitude of our applied friction can be found by taking the dot product between the negated friction direction and our anti-normal. We use this negated vector since this is the direction we want to apply the force in. I found that checking if the friction is 0 results in a lot less jitter, so we do that to avoid modifying the vector with garbage values. Finally, we can return the friction vector, scaled down by the time step. The result is a fully dynamic, interactable free body diagram, demonstrating friction assuming infinitely large coefficients. Thanks for watching.